So I'm going to get started. Today's announcements are, for those of you who missed the last two lectures, the website is www.orgchemboulder.com. And as a reminder, Monday is Labor Day, so we don't have any lecture on Monday. And also, to keep things balanced between the Monday and Tuesday recitation sections, we don't have any recitations next week. Okay, any questions about that stuff? Okay, actually one question for you guys. It looks like people have been signing up okay for Sapling. I've been seeing the membership sort of enroll, or like the roster sort of bump up on Sapling. I guess if you are having a hard time getting it set up, a reminder that the link in Canvas is the one that you need to access my Sapling course. So let me actually write that up here. So I've been getting a lot of emails about this, but use Canvas to access Sapling. Okay, I guess that wasn't a question for you guys, but just to preemptively answer the questions of anyone who asked that. Okay, so that's pretty much all I got for announcements. And so last lecture we got up through a fair bit of Lewis dot structures, guys. Okay, so we went through a bunch of examples. We saw single bonds, double bonds, triple bonds. We saw some lone pairs. And then at the end, we started looking at something with an overall extra electron on it. So just sort of a quick refresher from the very last example that I did. If you try to draw the Lewis dot structure for this, boron with 3 electrons plus 4 of fluorine with 7 electrons, plus 1 of, I'm going to draw parentheses around it so you can see it a little better, 1 of an extra electron, then you end up getting this structure. Okay, the lone pair electrons are going to get like more and more vague looking the faster I go here, but the bond electrons are the kind of the ones that we're focusing on. Okay, so we ended up with this whole thing, but because we have an extra electron on there, that tells us that we have an overall -1 charge on the whole deal. So we put a minus charge in square brackets, or on the outside of the square brackets around the whole thing. So this is saying we don't know exactly where it's located, but there is an extra minus charge in there somewhere. We could also draw this with the actual bonds shown, with the lines from boron to each of the fluorines and the minus charge there. Okay.
Where does the extra electron come from?
So good question. Most of the time it's going to be because there's some other positive charged thing floating around. Like for example, this thing is really commonly found in the company of sodium plus. So at some point sodium would have given up an electron to get its noble gas configuration, and this thing could have taken on an electron. It might not happen by exactly that method, but that's kind of the balancing that you want to think about there. Okay, so this is sort of useful. It tells us that we have a -1 charge on the whole thing, but it's not super helpful for being able to tell exactly which atom is going to have most of the negative charge on it. So for counting purposes, we need to figure out which atom is actually holding onto that spare electron. So we're going to calculate formal charge on each of these atoms. Okay, so it's pretty simple actually. Each atom for formal charge gets to count all of the electrons it has in lone pairs and half of the electrons it has in the bonds to it. I don't think I used this abbreviation last time. Lone pairs, I will very commonly abbreviate as LP. So each atom gets to claim all electrons in its lone pairs, which if you'll remember are the electron pairs that it's not sharing with anyone else, that it keeps all to itself, plus half the electrons in its bonds. Okay, so that's how you count electrons for formal charge. And then what you want to do is figure out how many electrons the neutral atom has. So number of electrons in the neutral atom based on where it is in the periodic table minus number of electrons when you're counting electrons for formal charge. So number of electrons associated with atom is going to give you the formal charge. Okay, so for example, if we're looking at BF4 minus, tetrafluoroborate up here, fluorine here gets to count 6 electrons out of its lone pair, or lone pairs, plus, sorry, I should put in each here, each fluorine individually, because we're doing this one atom at a time. Each fluorine has 6 electrons from its lone pairs. So if we're looking at, say, this bottom F down here, it's got 1, 2, 3, 4, 5, 6. And then it gets to count half the electrons out of the BF bond. Okay, so each fluorine, for the purposes of formal charge, gets to claim 7 electrons. Okay, based on where it is on the periodic table, how many electrons does fluorine have as a free atom? 7, right? Yep. Okay, so the formal charge on fluorine is going to be 7 minus 7, or 0. So for bookkeeping purposes, fluorine is officially uncharged in this structure that I drew. It needs 7, it's got 7, we're good. Let's do the same thing for boron. Boron has no lone pairs, so 0 electrons from that, because all of its electrons are shared. And then it gets to count half of the electrons out of all of its bonds. So it's got a total of 4 single bonds. That's 8 electrons associated with it. But it only gets to count half of those. So 4 electrons from the BF bonds gives us 4 electrons. We already know that boron needs 3 electrons if it's neutral. Okay, so we can do 3 that it should have minus 4 that it actually does have. Gives us a formal charge of -1. So that tells us that the negative charge in this structure is actually located on the boron officially. So if we want to draw a more precise version of what I drew up top here, we're going to not just throw square brackets and say, I don't know, it's in there somewhere. We're going to specifically put the minus charge onto the boron. Okay, so we're specifically going to localize that charge onto the boron. Okay, so this might be a good time to point out that you may have noticed I circle my plus and minus charges. Pretty much all organic chemists do that. The reason is that if you don't circle them, it starts getting a little bit visually confusing. Like if I didn't have this circle around the minus charge, that might look like a bond to nowhere. Or if I draw it close enough, it might look like a double bond to the fluorine, which is nonsense. So generally, you want to get in the habit of circling your charges. Okay. So pretty much like I automatically am going to draw a circle as soon as I draw a plus or minus charge. It's a good habit to get into. Okay, so questions about the calculations that I'm doing here. It's pretty simple subtraction. You just have to know how to set it up. But you may be asking, hold on, when we were counting electrons for octet last time, we counted all the electrons out of the bond. What changed? So just to sort of draw a comparison between this, we've actually covered already two different ways of electron counting. And if we want the atom to be as stable and happy as possible, we got to get both of them optimized. So two ways to count electrons on an atom. If we're counting for octet / duet, we're going to count all the lone pair electrons plus all the bonding electrons on an atom. And our goal here is to get the full set of 8. Unless it's hydrogen, of course. Meanwhile, for formal charge counting, we're going to count all the lone pair electrons. Those belong to the atom no matter what. And half of the bonding electrons. And this thing we're trying to optimize so that it's equal to the number of electrons in neutral atom. So in other words, formal charge should equal 0 for maximum stability. There's going to be tons and tons of cases we see where it's missing one or the other of these goals, but to maximize stability, you want both of these things to be satisfied at once. It needs a full octet and it needs a neutral charge. Sorry, I'm going to draw a little boundary there. Okay, so we can actually use these two conditions to figure out, in general, what's going to make particular types of atoms happiest. And when I say happiest, I tend to anthropomorphize my atoms quite a lot. Lowest energy or most stable is really what I mean when I say that. Okay, so carbon is most stable, or once, I guess, 4 bonds and no lone pairs, which makes sense. We saw one example with methane last time where carbon has 4 single bonds coming off of it. It's also true even if some of those bonds are part of a double or triple bond, it still has 4 total bonds if it wants to satisfy its octet, and it has 0 lone pairs. Nitrogen wants 3 bonds and 1 lone pair. I'm going to take a second and erase the other half of the board real quick if you guys want to take a moment to yourselves. Okay, so to get back into it, so carbon wants 4 bonds and no lone pairs. Nitrogen wants 3 and 1. Oxygen, as we saw in the example of water, wants 2 bonds and 2 lone pairs. And halogens, which if you remember are fluorine, chlorine, bromine, iodine, they each want 1 bond and 3 lone pairs. Okay, so we'll see plenty of less stable exceptions to these rules, but most of the time they're kind of transient, shorter-lived species. A lot of the time, sort of the starting and ending point of a reaction will have just about every atom with neutral charge and a full octet. Okay, so one kind of important exception. I mentioned that we usually are focusing on obeying the octet rule because we're not getting into the higher parts of the periodic table. So one case that we are going to see like sometimes pop up atoms in the 3rd row of the periodic table or below. Can actually go over the octet rule, do what's called violating the octet rule. We'll cover what's going on there for the time being. I'm just going to say by using d orbitals. If you've taken Gen Chem recently, you probably already know all about that, but if it's sounding kind of poorly remembered, then we'll get there in a little bit. So they can actually go over 8 electrons in their valence shell. So kind of a common example is sulfur can do this, although it doesn't have to. It can stay in the octet rule as well. But you will sometimes see sulfur doing things like this. Okay, so counting for octet, sulfur actually has associations with 1, 2, 3, 4, 5, 6, 7, or sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. But counting for formal charge, it still has 6 electrons and it wants 6. So it is still going to be neutral. Okay, so even if it's not obeying the octet rule, which it has the option of not doing, it's still going for a neutral charge overall on the sulfur in this case. Okay, questions about that example? Okay, cool. So just to sum up the rules for how to draw valence, or how to draw Lewis dot structures, I guess we didn't really talk about how to figure out the connectivity, like how to figure out how to put atoms together. I'll include that in this list though. So probably the most important place to start is only show the valence electrons, not the core ones. That's kind of a common thing where even if people know how to do it, sometimes they just forget to subtract 2, for example, for second row stuff. Atoms in the top row have at most 2 electrons in their duet, and they're most stable at 2. Atoms in the second row have at most 8. In their octet. And again, they're most stable at 8. I'm not going to write that out again, but just a quote from what it says above. Atoms in the third row or below can have more than 8. Whether they're most stable at 8 or not kind of depends on context. So if the only way you can figure out a structure that works is to squeeze some extra electrons into an octet of something in the third row or below, then that's just what you're going to have to do. If you don't already know the connectivity, like if you don't know what's connected to what already, start out by trying to put the atom in the middle that needs the most bonds. Or, we're going to cover this in just a second, the one with the lowest electronegativity. Okay, that says electronegativity. It's a little squeeze there. Okay, and then finally, if any atom has a non-zero formal charge, indicate it with a circled plus or minus. Okay, so the sapling homework has some examples of figuring out the connectivity. And there's some problems in the book. Really, the best way to get the hang of this is just to sort of work through and get the sort of practice down of how to build bonds and lone pairs. Okay, so questions about Lewis dot structures? Okay, cool. So what we're going to look at now is sort of a complication on the idea of covalent bonds. And I'm just realizing I did not move the camera over. Sorry to whoever's watching this at home. All right, I'm gonna just bring down the top part of the screen again. If you want to take a screenshot, I guess. Get out of the way there. Okay, and scoot it up. And there, okay. Okay, so polar covalent bonds are sort of exploring the concept that just because we're showing two electrons in the space between two atoms doesn't necessarily mean that they're actually being shared equitably. So you can think of the bond between two atoms as being sort of a tug of war. Even though they're both holding on to the two ends of the rope, one of them might be pulling a little harder than the other. So how strongly an atom pulls electrons towards itself out of the bond is called its electronegativity. And again, I'm running up against the edge of the board here. It's a long word, which is why I'm not going to write out the whole word anymore. I'm just going to call it EN, which is much easier to write. Okay, so in general on the periodic table, this is going to look like it increases up and to the right. So in other words, ignoring the noble gases, for which this is kind of irrelevant because they don't really form bonds because they don't need to. So fluorine is the most electronegative. So in other words, it pulls electrons towards itself the most strongly. And fluorine is up here. And then down here, francium is the least electronegative. And it's not really ever going to come up in chemistry that we're going to do because it's also highly radioactive, like most things this low down in the periodic table. But in general, the further down and to the left you go, the less these atoms are going to be interested in pulling on the electrons. So francium is the least electronegative. Okay, so for examples of an actual bond involving this, say we have a single bond between hydrogen and chlorine. I guess just for the sake of completeness, to get the full octet on chlorine, we also have 3 lone pairs on it. Did I see a hand go up a second ago? No? Okay, never mind. So HCl here. Chlorine is more electronegative. So chlorine's right about here-ish, ignoring the noble gases. Hydrogen's over here. So chlorine is more electronegative than H. So even though we're showing this shared electron pair existing as a line between hydrogen and chlorine, really those electrons are spending more than half of the time like associating with chlorine, or they're sort of getting distorted over towards the chlorine, and hydrogen is getting left with not as much electron density as it might like. So the electrons are closer to chlorine on average. So we have a bunch of ways to show this, depending on exactly how much detail we want to go into. The one that's sort of the most packed with information is something that's really hard to draw on the board. There's a few places in your book where they actually have sort of this rainbow-colored bubble around a molecule, and that's an electrostatic potential map. And that's where they've actually gone in and modeled this in a computer and figured out exactly how much electric potential there is at each place in a particular envelope around the molecule, and then used color to color code that. The best I can do in my notes around the board is just showing like stronger shading at this end of the bubble, and then it kind of fades off to nothing around hydrogen. So like stronger shading indicating higher electron density. On paper, more commonly, we're going to indicate this in a couple different ways. One is either by showing the 2 atoms in a bond still. We don't actually have like a true formal charge, like there's no actual full-on missing electron or extra electron anywhere, but there is a partial charge is how you can think of it. So the way that we show partial charges are with this lowercase delta. It looks sort of like a, I don't know, like a teardrop with a squiggle. So we can say either delta plus on the hydrogen, which is telling us there's a partial positive charge here. It's getting some of its electron density yanked away. And a partial negative on chlorine because it's got some extra electron density. So partial charges are one way to show this. Or we can do it by drawing a polarization arrow or a dipole arrow over the molecule. So the dipole arrow, at least in chemistry, always points towards the higher electron density, the more electronegative atom. And we can remember this because we put a little bar across the back end of the arrow so that this end looks like a plus charge. So this back end of the arrow is close to whatever has the partial positive charge because its electrons are getting pulled away from it a little bit. Okay. So questions about that so far? Okay, I am going to remember to move the camera first, and then I'm going to erase the other side of the board if you guys want to take another minute. Okay, so we've got a few different ways to indicate these bonds where even though it looks equal on paper, when we get into it, we can see that the electrons are not really being shared equally. So we can actually quantize a little bit. We can measure how big this inequality is. Because it turns out that polarized arrow that I'm showing, the bond between the atoms is actually a vector. So we're doing what's called, I don't think I've used the actual term yet, but the dipole is sort of what we're creating between these two atoms, which just means we have a positive and a negative charge kind of close by each other and associated with each other. So the dipole moment is a vector. So it's got both magnitude and direction, or size and direction. So this is pretty much just describing the amount of polarization. So it's equal to the size of charges times the distance between them. Okay, so in other words, you can actually get the same size of dipole either by having a longer bond, so bigger separation of charges, or by just having bigger charges. So if you've got two atoms here, I'm just going to call them X and Y that are bonded together. One other kind of way that people will sometimes use to like vaguely indicate the size of a dipole is just by drawing your delta plus and delta minus either really big or really small. So if we have like little delta plus and delta minus here, so small charges far apart, might have about the same as something where you've got two atoms with much bigger charges. So big delta minus, big delta plus, but they're close together. And obviously this is very non-numerical, just sort of from a very qualitative kind of standpoint. You can increase the size of the dipole by either increasing the size of the charges or the separation of them. Which, if you've taken physics, sort of makes sense. Like it takes energy to get those charges apart. That's the same as, I guess, it takes energy to create charges between, or create two charges that are separated in the first place. Okay. Question? Yep.
So it says about the same dipole. Is that because on both the X and the Y, there are equal charges or equal partial charges? But if X had a greater partial charge than Y, then the dipoles would not be the same.
Nope, so assuming that this is an overall neutral molecule, everything has to cancel out, so the whole charge on the whole thing, if I drew square brackets around it, it would have to be 0. Yeah, and so the same thing here. But so it's just saying like, and X and Y are not necessarily the same atom in this example as over here. I could call this like W and Z or whatever too. It's just saying like, if you've got, you know, a couple atoms that are separated a long way apart but with smaller partial charges, it's going to possibly be about the same dipole as bigger charges closer together. But I guess that's kind of pretty hand-wavy without plugging in any actual numbers, unfortunately. Yeah. Okay. Other questions about this before I move on? Okay, cool. So the other thing about vectors is, because they have a direction on them, they can cancel out with the other vectors. So vectors can cancel out if pointing in opposite directions or close to opposite directions. Okay, so kind of a classic example of this is if we draw a Lewis dot structure for CO2, carbon dioxide. Pretty much the only way to get everything neutral and with a full octet is to have each oxygen be double bonded onto the central carbon. Turns out that for reasons we'll cover in just a little bit here, the geometry around the carbon ends up being linear. So this bond has a dipole. I guess carbon is less electronegative than oxygen, so this dipole is going to be pointing out towards this O. And also, this bond has a dipole. Again, carbon-oxygen is polarized towards oxygen, is how we would describe that. So both CO bonds are polarized. In other words, they both have dipoles. But because they just so happen to be pointing in exactly opposite directions, for the molecule as a whole, they totally cancel each other out, which means that the net dipole on this whole thing is 0. Okay, so an example where that would not happen is, for example, we looked at the Lewis dot structure of water. Both of these bonds, again, oxygen is more electronegative than hydrogen. So that bond's going to be polarized towards the oxygen. That bond's going to be polarized towards the oxygen. These do not actually cancel each other out. They're not pointing in opposite directions. So and when I say cancel each other out, what I really mean is that you're just adding together all the x components of the vectors, all the y components of the vectors, all the z components of the vectors. And in this case, it turns out that you're adding like plus some number and minus some number, so they end up being 0. Here you're adding two vectors that are actually not exactly perpendicular the way it looks on paper here. We'll cover that next time, but they do end up adding up to something that has an overall dipole pointing that way towards the molecule. Okay. Yep.
Why didn't you draw the other hydrogen on the left side instead of like under?
Oh, so good question. It turns out they're both equally incorrect on paper. So we're going to look at Vesper theory and atomic geometry next time. Yeah, but neither one's really great. Okay, so I'm going to wrap up there and pick up on Wednesday next week. Have a good Labor Day.